Alright, hello again, and welcome back to more physics lectures. This lecture is going to be on color and reflection and refraction of light. So the last lectures also were about light, as I said, or maybe just the previous lecture. As I said in that lecture, there's a lot to talk about in terms of light, so this is more stuff to talk about. And beyond what I'm going to talk about here, pretty much anything that any of the topics that I'm going to go over or talk about a little bit here, you could have a whole course on these topics. So just like a lot of stuff in this course, we're just kind of scratching the surface of all of these things, right? But hopefully giving you some understanding the physics behind things like light, color. All right, so color, right? We all, most of us at least, experience color being red, blue, yellow, green, orange, all the colors in between there, and everywhere else. It turns out that actually seeing color and the experience of seeing color is very complicated and can be looked at in a number of different ways. So here in this lecture, I'm going to be telling you about color in terms of its physical properties. So that being specific wavelengths of electromagnetic radiation. So from a physical perspective, color is literally just a certain, say red is just a certain wavelength of the electromagnetic spectrum, and particularly it's a wavelength within the visible range of the electromagnetic spectrum, and it's somewhere around 400 nanometers, the wavelength. So that's like the physical explanation. The experience of it is much more about biology, physiology, neurology, and even philosophy still at some level, because what it is to actually experience color is still sort of a tricky question. Okay. But basically, experience of color, it's going to be different for different people. It may be that when you experience the color red, experience seeing the color red, it's a little bit different than when I see that color red and I experience seeing that color red. So just that as a caveat, because now we're kind of going to go more into, well, that physiological experience aside, what can we say definitively about color as being part of the electromagnetic spectrum? So so color in terms of light being part of the electromagnetic spectrum is literally just certain wavelengths within that spectrum. So I talked to you about the electromagnetic spectrum last time, and even said stuff about the visible part of the spectrum. And I told you that the whole electromagnetic spectrum just ran from very, very long wavelengths, like radio waves, to very, very short wavelengths, like gamma rays. And then in the middle there, not necessarily in the middle, but inside of that spectrum is visible light rays, or light waves, which are hard to say on the shorter or longer side, but in that 400 nanometer, 700 nanometer range of wavelength. So we also talk about, again, waves as in their frequency. So I told you last time too that essentially the longer the wavelength, the lower frequency of light that is, and the shorter wavelength, or the higher wavelength, shorter wavelength is a higher frequency of light. So color then being wavelengths from the sort of lowest frequency or longest wavelength of color is red, and just outside of red is infrared light, which transfers heat that we talked about before. In between the lowest frequency of color, that's red, and the highest frequency, there's all these ones in between, so you go, it's just like the rainbow. It is a rainbow. Red, orange, yellow, green, blue, indigo, violet, So violet's the highest frequency of color visible light, and beyond violet is what we call ultraviolet. And I told you guys a little bit about some of that, or a bit about interesting properties of ultraviolet light last time. But basically, it's just you get shorter and shorter wavelengths as you go from red to violet, and just after violet, the wavelengths keep getting shorter, and now you're into ultraviolet. And again, remember that the electromagnetic spectrum keeps going beyond that to shorter and shorter and shorter and shorter wavelengths. Okay. So this is kind of a reminder and a bit of a preview in this slide. A reminder in that this is what one way of looking at the electromagnetic spectrum is. Can be a little bit confusing because people don't really keep straight whether you put the long wavelengths on one side or the short wavelengths on the one side. So in this case, the spectrum is laid out from the shortest wavelengths, gamma rays, on the left, to the longest wavelengths, radio waves on the right. And sort of what's being pointed out here is really that that visible part of the spectrum is just this kind of narrow band in between ultraviolet and infrared. And also, as we'll see later in this lecture, if you use something like a prism, you're able to see or find out that white light, we experience as white light, like from the sun or from very bright or white lamps, is actually just a combination of all the colors of the spectrum. So basically you have wavelengths from red to violet all combined, kind of overlapping together. That makes up white light. And a prism allows you to sort of separate those, and you can see them as being separate wavelengths. And then also just point out that black is usually just the absence of any visible light. And so black, if something's black, doesn't mean that it's not radiating some kind of light, it's just not visible light, right? So it could be ultraviolet light, it could be infrared light, it could be other kinds of electromagnetic waves like microwaves, X-rays. All right, so let's try a little question here. What can the human eye not see? Infrared radiation, ultraviolet radiation, both infrared and ultraviolet, or neither infrared or ultraviolet? Hopefully it's an easy question, but go ahead and pause for a second and take a guess. All right, hopefully you know, or I reminded you or told you again in the last thing, that we don't actually see ultraviolet or infrared radiation. Radiation or light, you can say ultraviolet light, same thing, ultraviolet light, ultraviolet radiation. Yeah. So the answer would be C. We don't see either of those types of radiation, or either of those types of light. All right, so something that, so a little bit of a preview of what's to come later is that light, like I've been saying, is an electromagnetic wave. So it's a wave, it has a certain wavelength, just like any other kind of wave. It can interfere with other waves, it can reflect, it can refract, all the stuff that waves do. But as we found out through much trial and error, a lot of experimentation, light also is sort of like a particle, meaning it's also sort of like a billiard ball. And sometimes it's useful to think about light as a particle, sometimes it's useful to think about it as a wave. Turns out it's both, and we're going to get more into what that means in the next lecture. So just to give you a heads up, that sometimes like we think of light as coming in like little chunks, right? Just like chunks of light. And if we were to depict them, maybe we depict them as these little ovals And to indicate that it still has this wavelength sort of nature, sort of wave-like nature, we would draw, say, a red photon as being this oval, but kind of a pretty wide oval, right? Because red is the longest wavelength of light. Or we could draw the yellow photon, the yellow chunk of light, as an oval, but a bit skinnier than the red one. The green one would be a little bit skinnier than that. The blue one even skinnier than that. The violet one would be even skinnier than that, right? So you can think about them as like these kind of balls or these ovals, these ellipses. And the width could identify it as a longer or shorter wavelength photon. Yeah. Okay, so not much more on that right now, but more to come later. All right, so getting back to the human eye, or now we can kind of revisit the human eye after thinking about light a little bit more, or different colors that make up visible light a little bit more. I told you last time that the part of the eye that actually collects light is on the retina, and it's these photoreceptor cells, or the rods and the cones. And I also told you that the rods are basically just kind of light and dark, whereas the cones distinguish color. And as it turns out, you can see the cones, though not actually colored in real life, they're colored in this diagram on the left to indicate that there are essentially one kind of cone that is mostly attuned to the lower frequencies, being like red and orange, yellow. There's another cone that is very attuned to the medium frequencies, the greens, and there's one type of cone that is attuned to the higher frequencies, like blues and violets. So between those three types of cones, the low, the medium, and the high frequency ranges, they can pick up photons in those ranges, and altogether you get the full visible spectrum. So again, it's useful to think about light as a photon sometimes. So say a red photon comes into your eye, some red light. So from a red light, it creates a red photon. It comes into your eye. It goes through to your cornea, through your pupil, through the lens, and eventually it's focused back to the back of the eye. It's going to interact. It's going to basically hit one of those red cones, and the red cone is like, again, those photoreceptor cells are like antennas, so they pick up that red wavelength, and it'll send that signal then through your optic nerve, and your brain will essentially tell you that, oh, you're just seeing red. So, as sort of a consequence of that, or the way that our eyes are evolved to pick up different types of photons, the full spectrum that we see can essentially be built up by those three basic sort of colors, right? Red, green, and blue. So there's a number of different ways to talk about color, and we're not going to go into all of them for our purposes. We're just thinking about these, what we call the additive primary colors. So additive just being that if I have a red photon and I also have a green photon, then together those things kind of add together and can be interpreted as yellow. So like in this picture on the upper left, you have the three primary additive colors here, and in the spots where they overlap, you see all the sort of, or other secondary colors that they create when they overlap, and then when they overlap in more or less amounts, then you get all the rest of the colors basically in between. So, like I was saying, where red and green overlap, you combine to essentially create yellow. And the same sort of picture shown here, just a little bit more realistically with like theater lighting, where you have red, green, and blue lights, and with those lights you can essentially create whatever sort of colors you want overall. And again, just at the bottom here, I have a little diagram indicating that whether or not there is a red and a green photon that sort of simultaneously enter your eye and stimulate the cones, your brain's going to interpret that as yellow, or if it's actually a yellow photon that comes in with the wavelength that is yellow light, it's going to probably stimulate partly those red and partly those green cones, or those low and those medium frequency cones. Again, your brain interprets that as yellow light. So our perception of color really comes down to the fact that we have those three different cones, and from those, whether or not you're seeing some red and green overlapping or you're seeing yellow, your brain interprets that as the same thing. Okay, so some interesting stuff happens with color and objects, and I believe in the last lecture I talked to you a little bit about whether or not objects will transmit light, essentially allow light to pass through, or whether they absorb it, or whether they reflect it. And I think I also mentioned, or maybe I didn't, but now I'll tell you that an object will not necessarily absorb every wavelength in the visible spectrum. It might absorb some and not others. So it may be, as an example here, if you have a red ball, essentially what's making the ball red, or what causes you to see it as a red ball, is that shining, say, all of the light, all colors of light, so white light, it's a combination of all the colors in the spectrum. You shine white light on that red ball, then essentially all of the other colors, blue, yellow, green, violet, all those other colors are being absorbed by that red surface, and only the red wavelengths are being reflected or re-emitted. But just think about it as being reflected off of that surface. So we see all of these other photons come in, and only the red photons are bouncing off, essentially. So another interesting result of that is that, say, if you have a red ball and you illuminate it with white light, well, it looks like you would normally see it, because oftentimes you normally see things in white light, like mostly like sunlight. But if the ball is red and you illuminate it with red light, then essentially it looks basically the same, the ball itself at least does, right? Because in the first case, the ball is absorbing those other wavelengths and reflecting the red ones. In the second case, there's no other wavelengths to absorb, but it's still reflecting all those red wavelengths. So you're still seeing the same reds coming back. However, if you were to shine say a green light on that ball, a green is essentially completely separate from red, and so in that green light there's no red photons, there's no red wavelengths that are being shined on that ball. Therefore, there's nothing that's going to be reflected. It would only reflect those red photons. So that's why if you shine a green light on a red ball, it looks black, because there's no red to reflect back. So, and again, black is essentially just the absence of visible light. So this is something you call selective reflection. You could also think about selective absorption, right? It's basically objects are going to reflect certain frequencies of light and absorb other ones. So another example of this, or maybe a nicer diagram picture, is you have, say, like these three billiard balls. The black billiard ball is black because it absorbs all of those wavelengths. It absorbs all the colors of light. So there's no any photon that visible light photon that hits that surface is just absorbed by the material. Whereas the red ball absorbs all of them except for that red light which reflects. That's why we see this red. And a white ball would reflect all of them. Right? So shining white light on, all of the colors of the spectrum reflect, come back off, and we see all of them together, and the combination of all of the colors together is white light. Yeah. So a kind of a cool demonstration of this fact that combining all the colors of the rainbow gives you white is you can take a disk that's colored with all the sort of primary and secondary colors of the spectrum. I think you can just even do it with just the primary colors of the spectrum, red, blue, green. And if you paint that disk with the colors, and then spin that disk, spin it really fast, well, essentially what's happening is there's light that's hitting that disk, and say in the red area, that area again is red because it's absorbing all the other wavelengths of light and reflecting the red ones. Right? So white light hits that red area, and red light comes back off. And the similar things in all the other sections of the disk, right? But when you start spinning that disk, the same effect is happening, except for now when say the red light is giving off red photon, or the red section is giving off those red photons, it's moving so quickly that it starts to, for us at least, it will start to overlap with these other colors, these other sections. Essentially, our eyes and your brain, in a way, has its own frame rate. You can only see things at a certain speed, or yeah, it only acquires that visual information in certain little chunks, right? And so if it spins fast enough, then to our eyes, all the colors that are coming off of this disk, even though they technically actually are separated, will overlap for our experience, and we see all the photons of the same color, or all the photons of the different colors, coming essentially at us at once. The result of that, you spin this colored disk fast enough, it just looks white. So let's see that. So you got the colored disk there. He's got it on this like orbital sort of setup. So you get it spinning. Doesn't really get it spinning very fast at first, but is essentially winding up those threads, and then you can start to put tension on them. Release it. And here we go, right? So you can see there's color when it slows down a little bit, but when it's going really fast, it just looks like a white disk. Pretty cool. Right? So those colors are overlapping fast enough that your eye doesn't perceive them as being in different areas. It just perceives all of them coming out at once, essentially. Okay, so this idea of reflecting and absorbing, things reflecting and things absorbing different colors of the visual spectrum differently is, well, we can understand essentially some kind of very common questions that a physicist might get, or you might ask about light. One being like, why is the sky blue? Right? Good question. And the answer comes down to, well, essentially that the thing that makes up the sky, the atmosphere, is a gas, right? And that gas will essentially absorb and reflect light differently, or reflect sunlight differently than others. So however, in a gas, we don't really call it reflecting, because a gas doesn't have like a surface that you could imagine something reflecting off of, for the most part. The gas essentially is just those tiny little molecules or atoms. So instead of thinking about a pure like solid surface that light's going to come in and reflect off of, we call it scattering. So light will, say, come towards the atmosphere, and it'll hit one of the atoms in the atmosphere, and it will scatter off of it. So it's almost more like, again, like billiard balls, where light comes in, hits it, and scatters off. So it gets shot off in a different direction. Yeah. And as it turns out, the gases that make up our atmosphere, the O2, N2, things like that, they will tend to scatter high-frequency light, short wavelength light, much better or much more readily than they do with the lower frequency light. So what that means is essentially blue light is going to be knocked around much more when it starts running into the atmosphere than, say, red or green or orange. So essentially in the picture on the bottom right here, you see that when you look up at the sky and the sun's somewhere in the general overhead area, what you're seeing is, well, at least when you're not looking directly at the sun, I would not recommend looking directly at the sun, but when you're looking to the side, what you're seeing is light from the sun that's come down and it's hit the atmosphere, and the atmosphere is scattered mostly the blue light that's in that sunlight. Because the sunlight's white, it's made up of all the colors of the spectrum, a combination of the colors of the spectrum. So the blue light's scattered more, so when you look at somewhere in region in the sky, what you're mostly seeing is the blue photons that have been scattered by the atmosphere. Yeah, so that's why the sky's blue. Okay, so another interesting question. Why then are sunsets red? Okay. So in the last slide I told you, well, the atmosphere tends to scatter these, the higher wavelengths, like blue wavelengths of light, much more than it does the lower wavelengths. So what that means, when the sun is sort of getting low on the horizon, you could imagine in this picture, that picture is the Earth, that sort of circular thing is the Earth, and those little dots are meant to be the atmosphere around the Earth. And at this point, we're imagining that the sun is sort of on the right side here, and its light is shining, meaning that somebody sort of towards the top of the, or on the top of the Earth right there, is going to be seeing a sunset, right? It's the sun that's going almost below the horizon here. So when you imagine the light from the sun coming in, right, well, when it comes in straight to the side, again, if you were there, then what you're mostly going to see is the blue light that's getting scattered and coming down to the surface. Wherever you look in the sky, you're mostly seeing blue that's being scattered towards you. However, when the sun is low on the horizon, what that means is that the sunlight has to go through more and more of the atmosphere before it can arrive at the location you're at. And the result of that is that, since the atmosphere is scattering that blue light more and more, it means that by the time that that sunlight reaches you, most of the blue light has been scattered into all these random directions, and so you don't see it as much anymore. It's kind of all been diffuse, or it's become more diffuse, and there's just less blue light that's going to reach you out by the time that sunlight hits you. So most of those high frequency photons are scattered away by the atmosphere, and by the time the sunlight reaches you, it's mostly red and orange and yellow. Yeah. So there you go. All right, so we're going to get into the next part of this lecture about reflection and refraction of light. And just to tie that back, we've kind of talked about reflection a number of different ways so far. We're talking about light. Basically, when light goes from, sort of meets the interface between two mediums, like air and the surface of a mirror, or air and the surface of a pond, then it might reflect, which basically just means bounces off the surface, comes in, bounces, and goes back out. Right? Or if it comes down straight, bounces, and goes back up straight. Also said a good bit about light being absorbed by materials. So that's essentially going to happen when you have a material that light will hit, and it doesn't really reflect that light. That light won't pass through the object. So essentially the light gets absorbed by the atoms of that object, and it doesn't essentially just release those photons or that light. But besides absorption, when you have light meeting the interface of two materials, and it can still travel through the second one, so like light hitting the surface of a pond or a surface of water, light can bounce off that surface, can reflect, but it can also keep traveling through, and what happens actually in that case is what we call refraction. So when light goes moving from one medium into another, it turns out that it will bend, it will turn its path a little bit. We call that refraction. So we're all fairly used to each of these things, actually, we see them all the time, but probably more so with reflection, like mirrors, mirror or the pond, very still pond, Um, and with refraction, we also see that pretty regularly. Like you see this pen here, it looks like the pen bends as it goes. The part that's in the water looks like it's bent over. The pen's not bent; it's a straight pen. But what has happened is that the light that is leaving the pen, and it's going to come and eventually hit our eyes so that we see the pen. Right when the light leaves the or goes from being underwater to outside of the water, so it goes through that interface, it turns a little bit, and it actually bends down just slightly. And as it bends down, it comes to our eye, so our eye traces it back, and it actually thinks that pen is a little bit, essentially, the pen's now a little bit up higher than we thought it was. Or it seems like it's up higher. It's actually just still straight. It should be pointed out that reflection and refraction aren't like exclusive things. Oftentimes, both of them will happen in a scenario. So like the light that's being reflected off of the pond to show us the trees, in that example, that's not all the light that was coming and then reflecting off. Some of that light also refracts and goes into the water. So both reflection and refraction are actually happening in that image. We just don't see the refraction because we're not seeing the view from underwater. And then also just to point out that reflection and refraction are basic things that any wave will do. So we're going to talk about light waves and how they reflect and refract and what happens or what the consequences of those things are. But all other kinds of waves can do these things too. Water waves reflect, right? A water wave rolls into this onto the beach. It essentially sort of hits the sand and reflects back outward. Sound waves, seismic waves, all kinds of waves do these things. So we're just talking about in terms of electromagnetic radiation or light. All right, so first let's talk a bit about refraction. Right? So remember that bending or the turning of light as it goes from one material to another. And it turns out we already talked about refraction once before, and that was when we were discussing sound and how if you have someone, say, speaking on one side of a lake, it turns out that when the lake water, the air above the lake is a little bit cooler than the air higher up, the sound waves tend to want to refract and bend down towards the lake, and essentially they kind of skim along the lake and they can travel very far across that lake. Right. So again, well, maybe not again, I don't know if I mentioned that before, but the reason that light and other waves will refract is because of the fact that they move at a different rate when moving through different materials. So I mentioned before that light, the speed of light, is a constant in a vacuum, and there's no other materials around for light that light needs to interact with. So the speed of light is a constant in a vacuum, and that's like the limit at 300 million meters per second. That's as fast as light goes, as fast as anything goes. But if it's moving through air, it moves a little bit slower, or propagates a little bit slower. If it moves through glass, it propagates a little bit slower. If it moves through water, it propagates slower. If it moves through diamond, it propagates even slower. So the fact that it travels at a different rate in these different materials is essentially what causes that turn when it hits an interface. So if you can imagine, say like on the bottom left here, we have this diagram of two wheels that are attached to an axle. So there's essentially, you can think about it as like the front two wheels of a car or something like that. And in this case, the two sides of the wheels are coming at this interface. Say one side is a sidewalk and the other side is grass. So in that case, the car, or whatever that thing is going to be traveling faster. It's going to be able to travel faster on the sidewalk than on the grass. It meets a lot of resistance when it goes on the grass, so it slows down. But if that thing comes in at an angle, the idea is that the the wheel that hits the grass first, right, the wheel on the bottom side there, that one's going to slow down first. Right? So when, say, the bottom wheel slows down, the top wheel still is going at the same speed, what you end up getting is a turn. Right? The inside wheel slows down, the top wheel still is going at the same speed, so it turns a little bit. So that's actually a very good way to understand and think about how light will bend when it goes through a material. The same sort of thing happens with light, say, passing from air to water. Light goes faster in air than it does in water, so if it comes in at this angle, then essentially part of it is going to hit that water first, and it's going to slow down, and the faster part's still going to keep going, and we still get this turning effect. So that's the fundamentals of refraction. And just should be pointed out that refraction only occurs when light hits, or any wave, again, remember, but when light hits an interface at an angle. So like if you think back again at this picture of the two wheels, if you have a car or a cart or something, and it's coming straight at that interface, then there's no difference between the left and the right wheel when it hits that interface. Right? They both slow down at the same time, so there's no turning that's going to happen. Right? So this refraction only happens when you come in at an angle. Okay, so just to give you an idea of how much light slows down in different materials, there is essentially a numerical value that's given to indicate how slow light travels through a material. And that value is called the index of refraction. So the index of refraction is essentially just a ratio of the speed of light in a vacuum, so that 300 million meters per second, divided by the speed of light in that material. So if you think about that for a second, the top of that fraction is almost always going to be larger or as large as the bottom, right? So 300 million meters per second divided by something that's equal to or less than that. So what that means is that this fraction, this number, this index, is either equal to 1, we divide the speed of light in a vacuum, the speed of light in a vacuum, 1, that's the index of refraction of the vacuum is 1, versus you divide it by a smaller number, you're going to get a value greater than 1. So the index of refraction for a material is either going to be equal to 1, that's for a vacuum, or it's greater than 1. And essentially the larger the value is, the slower light is moving in that material. So here we just have a little table with some examples. So air, it actually is a little bit larger than 1, the index of refraction for air, but it's like 1.0003, something like that. So in air, light essentially moves at the speed it does in a vacuum. It's basically still the speed of light. Whereas in water, it moves a bit slower. In alcohol, even slower, right? So we get slower and slower and slower. All the way down here into diamond, moves pretty darn slow, actually. Right, so this is just a way of quantifying how fast light moves in material, or well, how much slower light moves compared to how fast it moves in the vacuum. Okay, so going back to that idea of like the pen and having how objects tend to, or seem like they may be bent when part of them's in the water, part of them's out of water, right? Refraction will do this, again, because light bends as it moves from one material to another. So when you're looking at an object that's underwater, there's sort of an illusion created that's your brain telling you the object is in a different place than it is. And essentially your brain is telling you the object is higher and closer to you than it actually is. So the reason being is, if we say look at this top picture, the actual fish is down here, and we see essentially like the light rays, or the light that's going to be, that's coming off of the fish, that will eventually reach our eyes and we can see a fish. But the light rays come off of the fish, and they're moving up, and when they hit the interface of the water and the air, right? That it's moving faster in the air. So again, you think of like these two wheels that are rolling along. The top wheel goes faster just before, or initially, when you hit that interface, the top wheel hits the air first, it goes faster, and bends the light to the left here. So the light's coming out, bends, and goes to our eye. But what our eye does, it doesn't know that that bending is happening, right? Our brain just takes that light and thinks, yeah, it came in a straight line. It came straight from the source. So our brain essentially projects back that light, or we call it like sort of tracing the light rays back, so that if you take those two beams that hit our eye, you trace them all the way back, then it seems like they actually focus right where that dotted spot. So it's a bit of an illusion, it's an image that you can see. It's not the actual fish. Yeah. Might be useful if you're ever actually trying to spear a fish for some reason, survival situation. Know that you should probably aim, well, you should aim lower than you think you should, or you think you're going to. Okay, so another interesting thing that is a result of refraction is something that we call dispersion. And dispersion is, like I showed you in the title, essentially refraction with a little bit of a twist. It's instead of something just refracting through one interface, it will then, if you allow the light to keep propagating and have another interface at an angle with that light, then it will refract again. So it's essentially like a double refraction. And the fact that refraction happens and the fact that refraction happens differently for different wavelengths of light. So just like different wavelengths are absorbed more readily or reflected versus absorbed in materials, refraction, essentially the amount of bending of a light ray, is going to be more or less depending on the actual wavelength of that light. So as shown in the picture here, if you have this, for the diagram on the top left, if you have a prism and you shine white light into that prism, then it turns out the red light that's in there, that's making up that, that's part of that white light, doesn't bend very much. It bends a little bit, or it refracts a little bit when it gets through that interface. Or I guess going this way or that way. So the white light comes in, the red light bends a little bit. Turns out that the higher frequency light, like the blue light, bends more, refracts more. So the result of that is that when the white light hits that interface, it spreads, it refracts each of them differently, and the wavelengths sort of spread out. And so if those light waves get to continue traveling along and hit another surface where they're going to refract, right? So another angled surface, then what's going to happen is just going to refract more. So you're essentially, now the blue is going to refract even more than the red again, and you're really going to spread that light out. So this is the reason why in the picture on the bottom here, if you shine white light into this prism, you see it sort of spreads out a little bit while it's going through, or on that first refraction, and then it spreads out more on the second refraction. And we can actually see all the different colors that are making up that white light. An interesting result of this is, well, explains why you see rainbows. So a rainbow is the result of the sunlight, white sunlight, that's going to refract into a raindrop, and it actually, some of that light, so like in this image you have the sunlight coming in, that sunlight refracts a little bit, right, so it spreads out those wavelengths, and then some of that light, instead of actually refracting and moving out on the other side, is going to reflect, and reflects back towards the bottom here, and that, well, once it hits that interface again, it's going to refract even more. So the white light comes in, spreads out a little bit, it reflects, spreads out more, and we get the full spectrum of like that violet to red light. So that's why you see the rainbows. And this is a nice example where, like I was telling you earlier, light or waves won't just reflect or won't just refract. Like in this case, when that sunlight first comes into the raindrop, not all of it is actually refracting into it. Some of it is just bouncing or reflecting off. And the stuff that does refract in, well, it's going to go and it's going to hit the back of the raindrop, some of that light is going to refract again and keep moving away, keep moving outside of the raindrop, but some of it reflects. And even more so, actually, when the light goes down and refracts again on the bottom, again, not all of it refracts, some of it reflects and is still actually in the raindrop. And when you get those multiple refractions is actually why you can get double rainbows. So you have this sort of thing, pattern repeating itself, and another spectrum or spread of light comes out. All right, so that was refraction. Right? So when light bends as it goes from one material to another, travels from one material to another. Now we're going to talk about reflection, and there's actually sort of two kinds of reflection, and we're really mostly just going to talk about one, but we'll point out the two kinds to begin with here. So there's specular reflection and diffuse reflection. So specular is essentially when light reflects off of a surface and bounces off in one direction. And so you have a bunch of photons coming in, all those photons bounce and go off in the same direction. So that's, like this sort of reflection is kind of usually what you think of when you think about reflection in general, reflecting. It's for like things like mirrors and very highly polished surfaces are actually technically doing this specular reflection. So just as indicated at the bottom here, bottom left there, all light comes in at one angle, it all goes out at one angle. That is opposed to diffuse reflection, which is essentially light comes in all the light comes in at some angle, but the surface is rather rough, and so the surface is not, it's not just a smooth thing, there's all these little bumps and dips and divots and whatnot, and so the light that's reflecting, each of it is reflecting off of at a different angle. Okay? So some light hits and it reflects back this way, some light hits and reflects off that way, so you get this very diffuse reflection. And in general, these are surfaces like mirrors, or not mirrors. Right? So a mirror reflects light back at the same angle. This stuff just essentially just kind of spreads the light out and it becomes very diffuse. That's why you call it diffuse reflection. So just non-mirrors, rough surfaces, that sort of thing. Generally the more interesting kind of reflection is this specular reflection. Right? So again, that's just usually more what you think about when you think of reflection. Right? So that's pretty much what we're going to be focusing on in the next couple of slides here, or when we talk about reflection. So in particular, there's something known as the law of reflection, and again, this is only particularly for specular reflection. I've alluded to this law a couple of times when I've said that, say, light comes in at one angle, bounces, and goes off at the same angle. That's sort of a very colloquial way of saying, or stating this law of reflection. The more technical way of stating this is to say that the angle of reflection is equal to the angle of incidence. So incidence meaning the incoming ray, light ray, and reflection, reflected, is the reflected light ray, so after it bounces. So in this diagram here, if we had light and it was being shined on this mirror surface, then that's what we would call the incident light ray, so the incoming light ray. And technically the angle that you measure the light coming in is you measure it from a perpendicular surface, or a vertical 90-degree surface from that mirror. So technically the angle that we're talking about is between that vertical line and the incident one. Right? So it's like this angle right here. So for reflection, this law of reflection essentially says that that angle is going to be equal to the reflected angle. And in this picture, that's what's shown here, right? The angle on the left of that normal line, of that vertical line, is the same as the angle on the right. And again, these are just some other examples of incident light rays, and reflected light rays. But they're all showing the same, it's all the same idea. Whatever the angle of incidence is, right? This image on the bottom left is maybe a larger angle of incidence, right? It's coming in at this lower sort of angle. but it goes out at the lower sort of angle too. Right? So same angle of incident as angle is reflected. Finally here, again, same idea. There's an incident angle, and now it's a very steep one, right? Or it's a very shallow, small angle. It's coming in almost more straight at the surface. But again, it comes out at that same angle. Yeah. Okay. So the fact that light will reflect in this way is the source of, well, why we see images generated from these reflected light rays. So think about when you're looking into a mirror, essentially your brain is telling you that there's a person. Well, you understand that it's not a separate person, but your brain sees it as just essentially a copy of you that's behind the mirror. And it's the same distance behind the mirror as you are in front of the mirror, right? That's what our brain tells us. So that thing is what we call an image, and that the image is created by this reflection. So it turns out there's a number of different things that we call images when we're talking about light rays, and later about lenses, things like that, and reflections. So in the basic sense, an image, what we call an image here, is the thing that our brain constructs from light that's been reflected, or refracted actually. We're just going to worry about the reflected things that are being reflected right here. And then beyond that, in terms of a flat surface, like a flat mirror, the image that's going to be created, that you're going to see, is always going to be the same size as the actual object, and it's going to be behind the mirror, the same distance the object is in front of it. So the way that, or the reason that we see like that is, again, our brain, when light comes into our eyes, our brain has no idea that light has been reflected, or that light has reflected somewhere, or maybe it's refracted somewhere. All our brain does is say, oh, okay, the light photon came in this way, let's trace it back and out, all the way out to where those photons meet again, and that's where I see the image. That's where my brain thinks the image is. So, like in this picture on the right, when you have a candle in front of a mirror, and you're up above that candle, you're looking down on it, what you're seeing is, imagine these photons coming off the candle, and they bounce, they reflect off the mirror. Again, this is our nice specular reflection here, so the angle they come in is the angle they go out. So we get those photons hitting the mirror, going back out, and those photons then hit our eye. But again, our eye just traces those photons back straight. And where they meet, since this is just a nice flat mirror, they meet at a distance that's the same behind that mirror as the candle is in front of it. Right. So this sort of idea of tracing light rays back is, you can call it ray tracing. There's a couple of maybe more terms for it, but essentially your brain does this, and then we also start using this technique to understand how refracting or reflecting lenses, mirrors, and things like that work, which I'll talk about more in a second. Ah, yes. Okay, so now we're getting to some maybe more useful things. Well, if you wear glasses, you've used your car's rearview mirror. All that stuff is very practical, and we're going to talk a little about lenses here to show not just an example of why some of these ideas are actually practical, but well, yeah, maybe we'll see that. Okay, so a lens is something that utilizes refraction, right? So we're going back to refraction, right? And that is the bending of light as it moves from one material to another. So lenses will use refraction to either focus light to a point, so a bunch of light comes into some lens and it might focus it, or it uses the lens might disperse that light. So a bunch of light comes in and it spreads out more. And those are basically like the two most common types of lenses. There's actually many more variations sort of on lenses, but these are the very most common ones. So the left is a converging lens, meaning converging because it converges light that comes in. If light comes straight into that lens, it's going to converge it to a point on the other side. So that's why it's called a converging lens. Technically, it's also called a convex lens because the sides are convex, meaning pushed outward. And you see the picture of it there, but just to be clear, a converging lens is going to be thicker in the middle and then sort of be thinner on the outside. And in the picture, the actual photograph on the bottom, you see an example of a converging lens where on the right side, there's been some light rays that have been generated. So like from, I don't know, very bright light, and you just put a screen in front of that light and cut little slits in it, so you just allow these nice light beams to come through, or beams of photons coming through. So the light comes in, and we see all these light rays coming in straight into that converging lens, and the light rays do exactly what you would expect them to do with a converging lens. They all converge to a point on the other side, the left side here. Right, so that's one of the main types, is the converging lens. The other type then is the diverging lens, also called a concave lens because it is, the sides are concave or crushed, pushed in. So the diverging lens again is similar, or it's thinner in the center and it gets wider at the edges of it. And it does the opposite. Right? Light comes in straight to a diverging lens, it'll spread out and go off in other directions, or spread away from itself in a sense. So in the photograph here, you see these three light beams coming in. They're coming in straight, and they spread out after they go through the diverging lens. Something else you might notice in these pictures is that, again, it's not just refraction happening in these pictures. You can actually see reflections happening and refractions happening. So the lighter light beams that you see are mostly due to reflections that are happening as well as this refraction. Yeah. And you can imagine why a converging lens will, or the shape of the converging lens is such that it will focus light. If you, again, just imagine light is coming in like a car, right? Like it has the two wheels on either side. If it comes in and it hits this converging lens, then say the bottom wheel here, my pinky finger here is the bottom wheel, will hit the transition first, and it's going to slow down, and it's going to turn the light as it goes, makes that transition. And then on the other side, after it continues to go through, now the top wheel gets out first, right? And since it's going to go faster when it gets out, it actually turns even more. So you get this thing happening where the light comes in, it bends on after it goes into that converging lens, and then it bends in again as it comes out. So we get this focusing and this opposite world. The same effect happens at the bottom. It turns in and turns in again. Versus with the diverging lens, you have the light coming in, and the top wheel sort of hits that interface first. So it will slow down and will turn the light up a little bit. And then again, the same thing happens at the next thing happens, it hits the interface again, and the bottom wheel speeds up first, and the top wheel is still moving slower, so it bends out even more. Okay. So these are very useful things. Largely, if you need glasses, you may be very appreciative of lenses. So, right. So what happens with people's eyes, like I mentioned when we last lecture, talking about the human eye, is that the front pieces of the eye, like the cornea, the iris, the lens, those are all essentially, their job is to focus light that comes into the eye onto the back of the retina. or onto the retina at the back of the eye. What happens, or can happen, is that the shape of the lens might be off a little bit. The number of different things. I'm not a biologist or optometrist, I don't know exactly how it works, but I know that there are issues where the cornea and the lens and whatnot are trying to focus the light onto the retina, but the shape is off such that you might focus the light actually inside of the eye, right, in front of the retina. Or you might focus the light behind the retina. So instead of all the light that's coming in sort of converging right at the retina, you get a very clear image. If all the light comes in and focuses in front of the retina, it's going to spread out again, or it's going to, all the light beams are going to try to converge, and then they're going to spread out again. They're going to hit the retina, it's not going to be nicely focused. Similarly, if it tries to focus behind the retina, then it just hasn't had a chance to come to it its focus, so you can still get a very blurry sort of thing. And as indicated in these diagrams here, the first picture is like the normal eye, right, where you're, or maybe the optimal sort of eye, where the light comes into the front of the eye, and it gets focused nicely right on the back of the eye, right in the retina. The second row here shows, apparently what happens for nearsighted people is that's when the light is focused inside of the eye. It's before it hits the retina. And it turns out that since your lens or your eye is focusing the light too quickly, essentially what you can do is use a diverging lens that's put in front of your eye, so that light that was going to come in, instead of just going straight into your eye and converging too quickly, when you use a diverging lens, it spreads that light out again. So now when your eye converges or focuses that light, it can actually correctly focus it at the retina when it hits the retina. The other end of that is farsighted, where your eye is focusing the light behind the retina, or would be focusing behind the retina. And in that case, essentially the light is taking too long to converge. It's not converging soon enough when it hit that retina. So what you can do is you can use a converging lens, and so that light comes in, your eye, if the lens wasn't there, your eye isn't curving it enough so that it focuses in the right place. So you put a converging lens in there, it converges the light a little bit before it hits your eye, so then your eye can do the rest of the work. I just have a quick little videos of this happening. So here we go. This is for farsighted. So the light is coming into your eye, the lens in your eye, and the lens that's in the picture here is meant to just be like it's the lens in your eye. And this circle on the right-hand side is your retina. So that's where you would like all of those light rays to focus. But in farsighted people, the focus is behind the eye, so the light beams essentially, or that light doesn't have a chance to focus soon enough to hit the retina and be a nice sharp image. So with this farsightedness, right, what you want to do is use a converging lens to converge those light rays before they hit the eye, or start to converge them before they hit the eye, so you kind of do a little bit of the work, then your eye does the rest of it. So you put that lens in there, and then there you go. Right? So now with that extra converging lens, the light that now enters your eye has already been converged a bit, so your eye converges it more, and we get a nice sharp focus at the back of the retina, or on the retina. Right, so then the other case was that nearsightedness, and that's when your eye is focusing the light too quickly, and all the focus is inside of your eye before it hits the retina. And so again, if you want to correct that, we can take a diverging lens and put it in front of your eye, so that instead of the light coming in as it would, it's spread out initially, so that your eye that's doing kind of that over-converging already will now converge at the correct spot. So now, well, it's still not necessarily perfect in this picture. You didn't do a perfect job of setting that diverging lens.
But you get the idea. Before, the light was focusing almost in the middle, and now we're getting much closer to focusing right on the retina.
All right, so last thing we're going to talk about here is telescopes. So, well, there's many kinds of telescopes, but a telescope is essentially a tool or instrument that allows us to see things that our eye alone can't see, or maybe just see things more clearly. And it does that, for the most part, just by allowing us to, or allowing more light into our eye than normally would enter. So one of the main limitations that our eye has is how much light can come in. And that is essentially limited by the size of your pupil. And your pupil can open and close a little bit and darken very bright light, but overall it's pretty small. One of the main ways that a telescope helps us see things better is by allowing more light using lenses to sort of converge and bring more light into our eye than normally would be there. So instead of looking up at the night sky, you see a bunch of stars, but there's also a lot of other stars you don't see because there's so little light coming from them that it's not really able to, not enough of it lands in our pupil to actually see it. Versus if you have a telescope, which has an opening much bigger than your pupil, it will capture more light and focus that into your eye so that you can then see those very faint stars. So one example of a telescope is just what's known as sort of a simple refracting telescope. And a refracting telescope really just utilizes a converging lens in the front and a diverging lens closer to your eye. So the basic idea is that, as shown in this diagram here, when light comes into that converging lens, the converging lens will converge that light, so it'll kind of pull it down, and so it bends in and goes towards that diverging lens, and the diverging lens then pushes that light out again, diverges again. In this case, it just bends it back to going straight, in the case your telescope working on. Right, so you have the converging lens, it takes that light, bends it in, the diverging lens bends it back out, but it's now in a more confined area so that all that light that came into the front actually can now go into your eye. So you've essentially taken all that light and squeezed it down, so now it can all, or at least the cross-section that it's going through, and now it can all go into your eye and you can see, intake all of that light. So examples, like a spyglass is a basically converging lens and diverging lens, all the way up to things like very large telescopes, optical telescopes, that can have lenses anywhere up to like feet, yards, like very large lenses. And the basic idea is, again, that the larger the lens, the converging lens at the front, the more light that you can actually collect in, focus down, and are able to see, essentially go into your eye then to see. So, like I said, or mentioned up at the beginning, there are many kinds of telescopes, this being the refracting one that we've talked about most here. There's also reflecting telescopes that, instead of using these curved, transparent lenses that will converge or diverge light as it passes through, you use mirrors. And when we talked about mirrors before, we were only talking about flat mirrors. And for flat mirrors, like I said, the image you see in the mirror is the same size as the image or the actual object that's behind the mirror. Right? Turns out, if you curve mirrors, either in a concave or convex way, convex way, then you have, say, like a curved mirrored surface. Instead of the light hitting that surface and reflecting back straight off, then the light that hits at the top will reflect down, the light that hits at the bottom will reflect up, the light that hits in the middle will reflect back, and you can actually create a where you can focus that light that hits the mirror onto a spot in front of that mirror. So if you have like a convex mirror, then all the light that comes in can get focused down to a particular smaller area in front of it. And it turns out that, well, that's what you call a reflecting telescope. And again, it's the same idea where you have this very large surface that can collect a lot of this light
and focus it down to this small area, except for not necessarily now onto your eye, now maybe onto a photographic plate or maybe a digital receptor, some many other fancier things. And it turns out that most of the very big telescopes that we have today are actually reflecting telescopes. And even beyond that, we've really just been talking about visible light here. But if you know anything about telescopes or anything about telescopes, you know that there's not just optical telescopes. There's also radio telescopes. There's infrared telescopes. There's gamma telescopes will pick up gamma rays. But again, those are all different parts of the electromagnetic spectrum. And so when you have like a radio telescope, again, it's just a big dish. So it's essentially like a mirror, but for radio waves, for the much longer wavelengths. Right? So it still focuses that electromagnetic radiation back to a point, or back to a focusing area. And yeah, so telescopes essentially, or as telescopes have evolved, we've really pushed the frontier in astronomy and allowed us to learn much, much more about planets, our solar system, our galaxy, our universe. Right? The telescopes in general have played a very large part in the discovery of how much stuff there is in our universe and how wild it actually is. All right. So that's it for this lecture. The next lecture is again going to be the final one. We're going to be focusing on light, no pun intended, and I'll use light as a way to transition into more modern ideas of physics. So, that's all I got, and have a great night. I'll see you next time.